the airport. What we have done is we have put a sign-off seat at the registration desk. So depending on when you want to go, if you can just write down your preferred time when you want to go, we'll try to see if we can group people together and then drop you off. Okay, so please during the break time talk to Anna and then write up your flight times and all, and then it'll be we'll be able to coordinate. So let's move to the next talk. Will be presented by Martin. He joined Dell Technology in 2011 after having worked as an HPC application specialist for 12 years at SGI and IBM. In 2019, he joined AMD as a senior manager and worked on porting and optimizing the major HPC applications to the Rome microarchitecture. He returned to Dell again in May 2020 as the HPC performance lead and distinguished member of the technical staff in Dell ISG. He owns a master's degree in physical chemistry obtained at the VU University of Amsterdam. Martin, I believe you were talking from Netherlands, am I right?
Yes, that is correct, DK.
Yes. Okay. So nice seeing you. You can share your slides and we'll see if everything pops up here well.
All right, well, let's get started.
Yes.
Today I'm going to talk about platform efficiency for large-scale workloads. I will start firstly with an introduction on Dell technologies in the HPC market. What a lot of people don't realize is that we've been doing HPC for more than 20 years. So with the rise of the Beowulf cluster, designed by Don Becker and Thomas Sterling at NASA, where they thought that they could use PCs for a fraction of the cost of a traditional supercomputer. Dell was actually very early to that as a major PC manufacturer, and we had our first HPC cluster commercially sold to Cornell University in 1999 already. We've since had a few successes in the top 500, top 10 entries at MCSA, Absenia, and National Labs. And a major thing was in 2005, where with the rise of the hyperscalers, remember that 2005 was the year that YouTube was founded, that those hyperscalers had a different need for large-scale computing. So we came up with a few designs for that particular market, and we also saw that those very dense designs were very applicable to large-scale HPC calculations as well. So we came with a separate product portfolio called the C series, where the C stands for cloud, already in 2008. I believe that we are now at the 6th generation of the C series, coming up next year. And since then, we've been quite successful. So we have had the biggest vendor in-house system in the top 500 that enabled us to do large-scale application studies and how the system behaves under load. We have the Frontera system together with TAC, and as of right now, we also have the largest system in industry at ENI in Italy. So we also believe that in three major pillars, that is democratizing, optimizing, and advancing HPC. Now, what we mean with that is that we want to make HPC easier to use. So we want to lower the learning curve for users to start using an HPC system. And that can be through a portal, it can be through the cloud, it can be through an easier way of deploying an HPC system. We also believe that optimizing HPC is very important, and we do that by continuously making improvements to our platforms for the 24/7 workloads that are used by HPC, and they are quite special compared to other enterprise users. The next one is that we believe in advancing HPC, so we believe that we should not reinvent the wheel. As the previous speaker said from Cornelis, we are also an open source company. We believe not in vendor lock-in, we believe in open standards. We believe in partnerships. Now, what I do as part of the Dell HPC engineering team is that we do 4 major things. So obviously we design, develop, and integrate HPC and AI systems. We do that through defining reference architectures. We tune systems for certain HPC and AI verticals. We work together with the engineering group, for example, to make sure that the HPC BIOS settings are tested and validated. We do joint R&D, both inside Dell but also with our technology partners. We do a lot of application and performance studies, and you can find all those studies at the website hpc@dell.com. So if you go there, you will find white papers, blogs, and presentations on various studies that we have done in HPC and AI. Lastly, we also work with our CTIO group to look in the future and to come up with new reference architectures and prototypes, and we evaluate advanced technologies there. The lab itself is also remotely accessible, so you can request for a user account. We can give you a tour, we can give you technical briefings if you are in the Austin area. So there are a lot of things that we can help you with. Here's a list of the various collaborations in HPC space where we work with, and you see that they are really scattered across the globe. Now, you're switching now to the main topic. What do we do in terms of MPI studies and performance evaluation? Because a large fraction or portion of the things that we do is to make sure that the application performance as itself improves, both on current, but also on the future hardware. And to start with, one important thing that we have come to realize is that, for example, collective MPI functions, they are a very important part of your performance. And I think this is well, knowledge to the majority of you. If you look at a collective MPI function like an all reduce or an all to all V, where you send data to every other MPI rank and also receive data from every rank, all the ranks participate in the same communicator of that function. Now, what you also have in a collective function is that you have an implied barrier. And because the collective MPI functions are so performance intensive, that has reached to the point that the major MPI libraries have multiple algorithms that are available to get better performance for your workload using one of the MPI collective functions. And you see examples here for Intel MPI, Open MPI, and MVAPage as well. Now, what you then see, for example, if you do your performance study on an application, and this is the NEMO Ocean model on, I think it was 640 MPI ranks. And what you see in here is a performance breakdown per MPI rank. So you see here MPI rank 0 all the way to, I think, 640. This is the wall clock time on the vertical axis, and the green area here is the time spent per MPI rank in the application. So you see that it is quite uniform except for this bump here, where a certain set of MPI ranks are spending more time in the application doing some computation. The other colors are time spent in various MPI functions. So the orange, yellow one is MPI all reduce. You see MPI receive is a major one, and there's a very small red and orange, orange for the I-send and the blue one for the MPI weight. Now, if you look then at the MPI all reduce, you can see because of the implied barrier and the collective form of the function that a lot of collective routines actually spend a lot of time fixing the load imbalance in your application. So that leads to performance being left on the table, you can say. Now, one of the things that I, for example, do is what can I do about this load imbalance? And one nice thing that you can do instead of using a blocking function, collective function with an implied barrier, you can also use a non-blocking function. So that is part of the MPI3 standard, as I think most of you know. The function name is then just the same as the blocking collective function, but then with the I prefix. So instead of all reduce, it is then becoming MPI I all reduce, and then with the arguments itself, you have a few extra ones because you also need to keep track of the request handle here. And with that, what you then can do, and here's a very simple example. If you then post the I all reduce here, similar to if you would do, for example, an I send or I receive point-to-point function, then you can overlap communication cost because of load imbalance by computation that can already be done on data that is not dependent on the all reduce operation to complete. So here in green, I can do something else, and then I here have my MPI weight with my implemented barrier on that request handle. And with that, if I look at your customer applications, I can actually remove a lot of barriers, and I can also shift the load imbalance to other parts of the applications, and then also sometimes improve performance considerably without doing too much effort. The other thing which then helps if you can do this, for example, if I do my computation and I send some data here to core 0 to core 2, and I then wait for the matching receive, what happens here is that during the wait, where you have your implied barrier, the MPI library is constantly polling the network fabric for incoming data, and that polling in itself, and I have later slides on that too, it is very CPU intensive. So what I'm looking at, for example, can we do this polling smarter? So for example, if it's worthwhile to switch during that polling to a lower P state, then we have extra power budget available to that other core that is still busy calculating computational data, and it can then execute a turbo state, so beyond its nominal base frequency, and therefore you could finish earlier and you get a possible speed up at the end. Right now, on current architectures, the P state switching is quite high. It is a couple of microseconds, and I consider it a little bit too high to actually make it worthwhile, unless you do a large collective operation with an implied barrier. Then it can be beneficial sometimes, but for point-to-point, it generally isn't. Now, what I've also seen is that a lot of applications have what I call problems with a lot of small MPI all reduces. So what I see here, and I have example here of OpenFOAM for certain workloads, or PAM crash, or Refresco. So it is primarily CFD where I'm seeing this, but I'm also seeing it in material sciences. If you look at the orange areas, you see that a lot of time is spent in small all reduce operations. And when I look at the message sizes all of them, or the majority of them, is smaller than 64 bytes. So that is really a problem, especially when you scale to larger clusters. It is only going to become worse because generally the message sizes also become smaller when you go up to a high number of ranks.
Martin?
Yeah?
Sorry for the just a quick question. Can you go back to the previous slide, please?
Sure.
So typically in the past, what we have seen is like, as you said, a collective is a like barrier, more or less, like it's a synchronizing operation. So load imbalances at the application level typically do reflect as more time spent in all reduce. So do you have an idea as to, for instance, if certain processes entered all reduce later? So let's say if 1,000 processes entered all reduce at time 0, and maybe like 20 of them entered at time 20, then that, like in a profiling tool, that would get reflected as time spent in all reduce. So is that what is happening here, or is it really that the all reduce operation itself is taking so long?
It is primarily load imbalance. I will show you later. I have a slide on that.
Thank you.
Okay. Then will continue. So when I look at the all reduce performance for various MPI libraries, and I have MFabH2 version 2.3.7 here in the larger blue line, you see that they are more or less the same. The only outlier that I'm seeing when I run on 16 AMD nodes with 2000 MPI ranks, that the outlier is OpenMPI for larger messages, unless I enable hardware collectives, HCall, so where you offload, in my case, to the HDR card, then they become in the same ballpark as the other MPI libraries. So this is not MPI library specific. That the MPI library itself has poor performance. Another example, and this one shows the load imbalance, for example, where I have OpenFOAM and I run on 5 Intel Ice Lake Xeons. You see the same thing with my MPI all reduce. It is everywhere approximately the same overhead, but you can see that my application profile, it is really spiky, so it shows quite a bit of load imbalance. Here you see that this MPI rank has a lot of time in application, therefore far less time in MPI wait all, for example. When I then look at my MPI all reduces, and this already shows part of the answer, in total I had more than 100,000 MPI all reduce calls for the duration of the job. But they were all very small, as I said on the previous slide, less than 64 bytes. My minimum time spent in MPI all reduce for this case was 30 seconds. The maximum time was 122. So you can see that there is a lot of implied waiting here because of the load imbalance, and it's a factor of 4 more than on the rank that has the minimum time. So if you want to improve the performance here, you should work on your decomposition and probably use a different decomposition model into OpenFOAM. Now, when I want to look at my real communication overhead, and I think this partly already answers your questions, that's what I'm then doing in my profiling library, where I am intercepting the MPI all reduce function. I do then an implied barrier here. And that means that every rank hits this barrier. And that then means after they have all hit this particular barrier, that my all reduce itself is then done on the perfectly synchronized data. I mean, they are all starting their all reduce at the same time. Now, when I then look at my library, and I here have an example of the MOM ocean model benchmark that I run on 1152 MPI ranks, you can see that my all reduce is again quite significant. It's in orange. MPI overhead itself is quite high. You see that there is some load imbalance here as well. Now, what I then can do in my library, because of this function, I can distinguish between what I call exec all reduce. So that means the actual all reduce operation, or the wait all reduce, and that is time spent in all reduce because of load imbalance. So I have to wait for other ranks to hit that barrier. Now, what you then see, and it is very hard to see, so I will zoom in a bit here, but you see that the actual execution time is in MPI all reduce is very, very small. So out of my time that is somewhere between 191 and 463, they are all spending only, let's say 10% at minimum doing the actual all reduce, and the rest, so that is 90%, or yes, sometimes even 95%, I think, if I do the math from the top of my head, that is then done in spent in waiting for the load imbalance. Now, I have to say all these things actually can sometimes work, because here I have an example. If you do hardware collectives, where I have a HDR200 card and I run FASP on 4 isolate nodes, so a quite small job where my data is there is okay-ish, and there is a lot of collective MPI communication, which you then can see if I enable hardware collectives, and here are various ways to do that on MPI libraries. I can actually get a 20% speed up. So you can see that my exec, so that is time spent in the MPI function. So those are the dark colors, so dark green, dark red, and dark orange, that they are significantly less in the HCall enabled run. And you can also see the yellow here is much less. I think this was MPI barrier, which is also a collective operation that can also be sped up by hardware collectives. Now, to the last part of my talk, and I realized that I only have 6 minutes. I think that message rate is becoming more and more important, because we get more cores per node, and we also get more bandwidth per node, but it is not going up to the same speed, because here we have 8 times more cores, while we only have 4 times more bandwidth. So that is a bandwidth problem, as people keep saying. But we have these extra transfers or endpoints that we also need to manage. Now, the good thing is, well, we are familiar with the latency and the bandwidth numbers, and I've here compared starting with Connect X3, so that is FDR InfiniBand, all the way to Connect X6, and I also did put in 100 gigabit omnipath. At the latency and bandwidth, latency has more or less stayed the same, sometimes increased a little bit. The bandwidth has improved, but the real improvement is in the message rate. So you see that modern InfiniBand technologies are actually capable of sustaining the extra message rate that is coming from the extra cores on the nodes. Now, more cores also helps your message rate for your small messages. And you can see here when I decompose in various ways that I still get an improvement. So if I run on 128 cores per node, your message rate linearly scales for small messages. If I go to 64, it is half, and same for your 32 MPI ranks. it doesn't give me extra bandwidth, which is what I expect. So even a single core, or sometimes 4 cores per node, are able to fully saturate the bandwidth of an InfiniBand card. Now you would say, why is this important? Well, the reason is that I am looking for the maximum capable bandwidth of a system, because I believe that in HPC, a lot of applications are still primarily bandwidth limited. So not only inside the node, but also outside the node. And that means that I have to look at bandwidth, the most optimal bandwidth for my decomposition that I'm going to use in terms of MPI ranks, and then a certain number of OpenMP threads per MPI rank. So you see on an AMD EPYC system in either green or blue that it is quite spiky, depending on how much threads I use per node. And I have to add that what I did here, that everyone had its optimal placement. So I always make sure that I get the maximum memory bandwidth. For Intel, it is much less of an issue for Ice Lake. And you see here for AMD that you get maximum bandwidth here on either 16, 24, 32, or 40 cores. And this is very important. And it is 30% better than on 128 cores, for example. And you can see that in applications like WRF, when you run on 30 times 4 threads, then you get much better performance than if you run on full MPP mode with only one thread per MPI rank. Now, lastly, is that we look also at MPI power consumption. As said, if an MPI application or MPI function is in a barrier, it is constantly pulling the network fabric. And what we are doing here is that we have run the OSU barrier benchmark for a certain duration of time. And I am running an external profiler that is then measuring my socket power consumption 4 times, or this was even more, I think this was 10 times per second, where I then measure my CPU power consumption. And you can see for almost all MPI libraries, it is using full power of the socket. I have a 205 watt TDP CPU, and it was using full TDP to only sit in a barrier, which is, you can say, also a waste of power to minimize latency, obviously. But when you're in the majority of the time doing a barrier and you don't have perfectly synchronized data, then you are wasting a lot of energy. And you can see you can overcome this. Yes, sometimes if you enable hardware collectives, so where we offload to the card. And in this case, Intel MPI has done something smart where they are able to do the same barrier also much quicker than the majority of the other MPI libraries. Although MUG'22 more or less has the same performance as Intel MPI, but they are using it or doing it with 25% less power. You can optimize Intel MPI even more, so you can get it even further down, but that is then at the expense of the barrier performance, right? So that is something to keep in mind. Same thing, for example, for all-to-all, where all the MPI libraries are still using full TDP power, but as said, this is a very performance critical and a computationally intensive task to send and receive data from all MPI ranks. I should add that you can get better performance if you switch to a UD transport, and especially that is quite easy now on MUG'22 version 3, where you can choose UCX as underlying transport library, that you can get better performance, lower latency if you enable the UD transport. All right, that brings me to the end of my talk, and I gave you some of an overview of the things that we are doing at Dell, particularly around the MPI. As said, you can find a lot of information online. We have a HPC community where we have 4 events per year you can register for free of charge. You can find a lot of our white papers here at hpc@dell.com. If you want to know more about the Innovation Lab, then this is the link to find it. Thank you.
I actually have a question. For the performance graph of bandwidth of different number of cores, where we find 16 or 32 or other process numbers that has the higher bandwidth performance. What is the strategy we use to map the cores to the process to the physical cores? Are we doing it with a linear pattern that map cores from core 0 to core 1, core 2, core 3? Or are we doing this with a scatter pattern, like crossing different CCX first and then go to repeat it again?
Now, what you typically do is indeed that I use scatter, because as said, I believe that every MPI rank should have maximum performance, and then within the MPI domain, you want to have all cores as close as possible to the MPI rank, because if they share the L3 cache and they share the same memory controllers and local memory, then you get better performance.
I see. Thanks.
Okay. And
Martin, so you have talked about the impact of imbalance on all reduce. What is the root cause of this imbalance in your opinion?
If you have an imbalance, then it is often due to poor domain decomposition, or people are not using the right amount of MPI ranks for the problem.
Great, thanks.
okay. Are there any questions on the chat from remote people? Okay. Okay. So then, thanks again, Martin.
You're welcome.
Yeah. So we'll move next to an in-person talk. Will be presented by Christopher et al. From